Hi, in this video, I'll be talking about differentiation and the notion of a derivative. We've talked about continuous function and now we'll move on to differentiation. So, let's start with an example to illustrate what do we want to find when we are taking a differentiation operation. Imagine you have the graph of y equals to fx and you know that there's 2 points over here. You want to find the slope of the tangent line, and so we want to know how to approximate the value. Well, if you can draw a line between these 2 points, you get a slope, and this is called the secant line. And as you move this point nearer towards the point you want, x, for example, drawing this new line, we can see that this gradient of this line is approaching the gradient of the tangent line. And so if we draw more and more points closer and closer to x, and we draw its secant line, that means the line connecting these 2 points, it will approach the gradient of the tangent line. And so what we want to say is that as h approaches 0, h being how far it is from x, the slope of this line equals to the slope of the tangent line. And therefore, the gradient, which is the slope, equals to the limit as the change in x approaches 0 of change in y over change of x. And you can also write it as the limit as h approaches 0 of fx plus h minus fx. Fx plus h is the y2 minus the y1 over x2 minus x1, and this is just h. And so we can define the derivative at the point A to be the limit of h approaches 0 of fa plus h minus fa over h. Or by substitution, you can just say as x approaches a of fx minus fa over x minus a. And so this is the derivative at a point A. And so if this limit exists, we say that f is differentiable at point A. And so you can do a few following interpretations, such as finding the slope of the tangent line, or we can actually just say it is the slope of the graph. They are equal in interpretation. And if you do physics, you can also take this slope of the tangent line as the rate of change of x with respect to x. Or you can also call it the derivative, and f is just said to be differentiable at that point. The following exercise illustrates how to find the derivative from first principle before we move on to actual differentiation formulas. But the actual differentiation formulas are just proven using first principle as well, and they're just, because you already proved them, you can just use them easily. Read through the exercise to get a better grasp of differentiation using the limit principle, and we'll move on now. So we have proven what it means to be differentiable at a point, but let's say now that this a, this value is defined on an arbitrary value on an appropriate domain. What we want to say is that f prime a is the limit as x approaches a of fx minus fa over x minus a. For different a, we get a unique value of f prime a because if the limit exists, it is unique. And so now we can view the function f prime x as a function on the domain where the limit exists. And so now we are referring to differentiation as a function, and we write it notationally like y equals to fx. F prime x can just be written as dy dx, which equals to fx differentiated with respect to x. And this dx is known as the differentiation operator. And thus, if we want to evaluate at a for a certain point, f prime a will just equal to dy dx evaluated x equals to a. And so now, this f prime x is actually a derivative function of f. For example, fx equals to square root x, defined on x larger or equals to 0. If you want to find the formula, it is actually just you have to use the first principle, and you can work it out to see that you get 1 over 2 square root x. But in this case now, you can see that x is no longer defined, the derivative is not defined on x equals to 0 because here will be infinite. And so while the original domain was x larger or equals to 0, the derivative function may have a different domain. And so you need to check clearly. And so, since it is differentiable for all x larger than 0, we say it's differentiable at every point in the interval 0 to infinity. I hope this is clear, and you can relook at this if you do not understand. And now a bigger theorem is that differentiability implies continuity. And so if f is differentiable at point C, f will also be continuous at point C. You can just imagine if it was discontinuous, you are unable to draw a tangent line at any of the points. And so, at the discontinuous point, I mean. And so, then if you cannot draw its tangent line, it shouldn't have its derivative because the limit won't exist. And so if you just take the contrapositive of that idea, it means that if it has a derivative, you can draw the tangent line there. And so it is continuous at that point. And the proof follows from what I've just said. Given that it exists, we must show that the limit is fc. But we can convert this by substituting the limits from this equation instead. And now we know that fc plus h equals to fc plus h minus fc. If we divide this by h and multiply by h again, we can see if we take the limit, this part will be some value, and this will go to 0. And so this value will just equal to fc, and hence proving that it's continuous. And hence differentiable functions are always continuous. And so when we used to have the properties of continuous functions, such as adding them to be still continuous, multiplying in still continuous, we have the similar properties for differentiable functions. And the derivative follows as following. If we were to multiply a scalar, the function will still be differentiable, and its derivative is the scalar times the derivative of f. Adding them, you can just piecewise differentiate them. But for the product and quotient, it's a little bit more tricky. So you differentiate one of them and multiply by the other one, keep making, and then you add f and you multiply by the derivative of g. The book has the proof in Thomas Calculus, and I urge you to read it to have a better grasp. But you should be able to familiarize yourself with this formula after doing more practice examples. So do remember to practice up. And this allows us to also form more types of differentiable functions, such as polynomials by adding and multiplying, rational by adding, dividing and multiplying, or anything. We can also prove that trigonometric functions are differentiable, and these are the derivatives. There are also exponential functions and logarithmic functions. I'll dive deeper into this type of functions in later videos when we talk about integration. But do take note that there are many types of differentiable functions that we commonly use, and most of them, if they are very nice functions, they will have a very nice formula for us to use often. And so, practice more and you'll be familiarized with the different type of differentiable functions. Next, we move on to proving we know that composite functions are continuous if both functions are continuous. We want to have a certain notion for differentiability as well, and it is true. Differentiable functions evaluated at the point x, when you take the composition, is still differentiable, and this is the derivative. It's a very nice way of saying dy dx equals to dy du times du dx. You cannot treat this as a ratio where you can eliminate the numerator and denominator, but you can write it in a form for easier to remember purposes. And so the proof takes a bit more technical skill, but the idea is to create an error function and see that when you multiply them together, you get the following expression. I'll leave you to read the proof on your own. It is not too hard to follow, but you have to take note of the different notations that I've used. But either way, you can use this formula to get the derivative of the composition of functions, where you differentiate the f and evaluate it at gx, then you multiply by the derivative of g at x. Practicing more will also help you remember, and reading the proof might actually get you a better understanding of the chain rule. Now we take a look at this example to bring the notion of implicit differentiation, which is built upon the concept of the chain rule. For example, you have the function y squared equals to x, and they ask you to find its derivative. Well, you won't be able to differentiate this normally with the usual understanding, but you can take the square root and y1 will equals to square root x, or you can just say y2 will equals to minus square root x, and now you got two separate functions as the graph looks like this. So this part will correspond to x square root x, and the bottom part will correspond to minus square root x. And so dy1 over dx will have one type of different derivative, and dy2 will have another. And then if you want to evaluate them, you need to specify which branch of the graph you want to evaluate the tangent. For example, the upper branch or the lower branch at the same point x equals to maybe 2. But another way to do this is to treat y as an implicit differentiable function of x. And this means that you treat y as a function of x and just differentiate using the chain rule. So you just differentiate with respect to x first. This d dx can be converted to a d dy, but you have to multiply it by dy dx. By treating it as an implicit differentiable function, it means that this dy dx exists, and so the equation still holds true. And hence, when you differentiate now y squared with respect to y, you can easily do it as 2y, and so you divide them over. But y cannot equals to 0 in this case. And you see, if that y cannot equals to 0, x also cannot equals to 0, and that's why these formulas holds true as well. And if you take any point now, you just need to specify the point again. You can easily calculate the derivative. And so this is what it means to be implicit differentiation. It means that you do not write it in a closed form, an explicit form in terms of x only, but you are able to write it in either in terms of y or x or both. And so the idea is to just differentiate with respect to x, and then you collate all the dy dx term and solve for dy dx. The following example illustrates the point. As we just differentiate with respect to x, this we have to differentiate with respect to y, so we multiply by dy dx to convert this to a dy. Similarly for the rest, and if when you're done, you just collate all the dy dx term to one side, pushing all to the other, and solve for dy dx. And so notice that the derivative involves both variables and not just the independent value variable x. So you can see the utility in using implicit differentiation, because it gives you another way of formulating what the derivative is without explicitly finding it, because it might be hard For example, if this was y 3 over 2, then you need to take the power of my 2 over 3 over here, and then you need to do a power rule and more. And so with implicit differentiation, it makes it easier. The last part is just a simple part where we just talk about higher order derivative. And so while we keep differentiating once, it is known as the first derivative. And we can just differentiate n times, and they'll be known as the nth derivative of f. And if all of this, if the n derivative exists, then we say n is n times differentiable. And we write it notationally as follows. And the idea of higher order derivative is really just differentiating multiple times. So if you take this example, f prime x is cosine x minus x squared. If you differentiate this one more time, it will be minus 2 sine x minus x cosine x. And that is just the second derivative. You can differentiate it again to be the third derivative and continue. And so, this is the end of the notion and definition of derivatives. In the next video, we'll talk about its application and how we can use and the importance of differentiation. Thank you for listening, and I'll catch you in the next one.